Hi, I welcome you on the last presentation before our lunch break. And this time we're going to hit a little bit, I would say, more ground topic. So, because like behind every model, behind every inference, we have a bunch of data and a bunch of mathematics statistics coming. So it's always a case to choose the good representation, good classes, good features for models, for training our models, and then for analytics. So we have Sergei that is going to talk about feature selection and how to tackle the problem in an optimized way. Sergey, welcome on the stage. Go for it.
Hi, hello. Thank you for the introduction. Hi, everyone. Thanks for being here. So, yeah, as it was just said, I will be talking about more about analytics than engineering, maybe in my talk, and the topic is the problem of selection of the features that can be used for better model performance and that have the that contain the highest amount of useful information within themselves for the target that we're trying to predict. And mostly that talk will be considering only binary problems where the target variable can take only two values, and what makes it also different from some other popular feature selection methods is that it works well in case of imbalanced data sets. I will talk about what that actually means and what an imbalanced data set is. So let's start, I guess, from the few common words about why it actually matters. Just for the background, so we are talking about building a machine learning model, and this is like a preliminary step to select the representation of objects that we find useful for our model. And why this is a very important step? Well, because it actually, due to several reasons that you can see on the slide. The first one is that it just reduces overfitting and thus improves generalization properties of the model, which also improves interpretability, meaning that models with compact representations of the objects are easier to explain and easier to understand, to analyze, to visualize. It speeds up training for obvious reasons, less parameters, less degrees of freedom, less hyperparameters to tune. It improves stability of the models that we build, and that's actually connected to the first reason that given that it reduces overfitting, usually within the smaller sets of possible values, it's easier to find the optimal set of parameters. And it mitigates multicollinearity. So when the representations are large, they tend to be not actually orthogonal to the features that build up the representation tend to be related to each other, which also affects performance of models because it allows for different analytical representation to be equivalent, and that makes it harder to optimize some quality of some metric of quality. Okay, so that's why that matters. Let's now consider several methods. Like they can be all split into 4 groups. The methods that allow to select good representations of objects, good features. The first group is feature extraction, for example, principal component analysis that was invented a lot of years ago, like by Carl Pearson. So it's a very classical approach that aims to orthogonalize different features to solve that multicollinearity problem, like in a very straightforward way. And extraction usually means that we build new features from existing ones. Then the second one is wrappers. That's an approach that is based usually on some model that we know we are going to build, and we just select the subsets. We just test different subsets of features one after another in some way, like greedy, for example. And we just check out which gives the best quality for the model that we are going to build. This is usually the most inefficient one because it means that we need to train and test our model many times. It works more or less well if the model is simple, but if it's a large neural network, then it's a waste of resources. Then the third group is so-called embedded methods, for example, lasso regression. That means that when we build our model, we automatically, like for free, get feature selection, because lasso regression tends to make some coefficients of our linear regression equal to 0, which basically means that the corresponding feature does not take any part in inference, and that's in a sense also feature selection. And the other group is so-called screening. That's when we do not try to extract new features. We just work with those that are already present to us. And that's a purely analytical method independent of the model building. So it can be done fully as a preliminary step to model building. And it's just an approach when we test each and every feature that we have one after another independently from each other. That has some weaknesses as well. For example, some features can work well only in combination with others. So, for example, it's easy to think of a feature that is itself independent from the target, but conditional on the distribution of some other feature. It actually impacts the target value. But in those cases, we can try to combine those features into like some vectors and consider a screening procedure on the combinations as well. So yeah. Now let's talk about what is actually important about binary case control studies and why they are different. And because that's actually where screening methods are the only ones that really work well in like statistically grounded way. So binary case control studies and imbalanced data sets, it's when basically the share of objects that belong to one of the two groups that we have does not really represent the probability of the objects belonging to the corresponding group. So what that means? For example, you can think of a medical case control study when you have 1,000 patients. Let's say 500 of them have some disease, 500 of them do not. And you are trying to understand which factors affect having this disease. So obviously the probability of having disease is not equal to 1 divided by 2, which is the number that you get if you just divide like the share of the sample that has disease by the total size of that sample, because you just selected those patients in a way that half of them represent one group and half of them represent another group. So that means that share of the objects belonging to some group does not really reflect the probability. And in that case, it's easier to think of such samples as actually two independent samples. One of them from distribution of some objects conditional on belonging to the first group. The other one is distribution of the objects conditional on belonging to the second group. One is defined here as y equal to 0. The other is defined here as y equal to 1. And the other situation when this setup is actually widespread is any situation when events of interest are actually rarely encountered. So like fraud detection or churn prevention in telecom or any other like credit default by a financial entity, any situation when the events are rare, they usually tend to benefit from setting up samples in an imbalanced way, and because otherwise traditional models, they just tend to overfit the dominant class and does not bring any useful insights about the minority unless you just tweak somehow the learning process. So that's it about the motivation, I guess. And here is about what we are going to see. So what we are going to see is just a screening-based, model-free approach to solving the problem of selecting features based on imbalanced binary datasets. And some of the properties of that method is that it is very lightweight, it is very simple, and it is really very easy to understand. It is statistically grounded in the sense that you can actually even prove some theorems about some so-called sure screening properties that based on some assumptions you will get the right set of features and filter out everything that is really does not impact the target variable of interest. And it is transparent, which is also related to it being very easy to understand and easy to implement. It's easy to explain as well to stakeholders. So the idea, there is some formula, some proof actually, but the idea using words is actually very simple. So imagine that you have two groups, one like patients, for example, that have some disease, the other that patients that do not have that disease. And imagine that you take some factor and take a look at its distribution within both samples. So the idea is that if this distribution is very close one to another, then the target variable of interest, the variable of having a disease in that case, really does not depend on the corresponding factor. So here is an example. If you, for example, take an age of the lottery ticket buyer, and then you consider the sample of people who won in the lottery and people who lost in the lottery, then if the age of the person who bought the ticket distributed approximately in the same way in both groups, then it means that age does not affect the probability of a ticket being a winning one. If, let's say, you find out for some weird reason that age is distributed completely differently, then probably being of some age affects the probability to win or to lose in the lottery, which is probably not the case. Here is the explanation, the mathematical explanation, and the idea how to quantify that fact of two distributions being close or not close to each other. So the fact is that some feature xk, if it is independent, then you can prove that the distribution of conditional distribution of it be if the corresponding object belongs to the first group is equal to conditional distribution of it being for the objects from the other group. And the idea to quantify it is to use statistical distance. So there are actually some not metrics, because they do not really satisfy all the properties of metrics in mathematical sense, but some popular distances that allow you to measure the like how different are two distributions, and we will consider just two examples. So basically how that looks like. When you have some sample, you can build like on the left-hand side, you can see, for example, a couple of histograms that represent some estimations of probability density or probability mass functions. In case of the feature being a continuous one, a histogram represents some approximation to probability density function of it. And in case of the feature being a discrete one, it represents an approximation to probability mass function. So if you have two histograms, you can measure distance in the way that is written here. So in continuous case, you need to calculate some approximate integrals. In case of probability mass functions and discrete features, you can calculate just some sums. Here, Pj represents the probability of the feature taking value j, for example, within the group y equal to 0, qj the same thing, but within the group y equal to 1. And to build those estimates of probability mass functions, you just need to basically take the corresponding frequencies within your sample and plug them into the formula for the distance, which will give you the so-called plug-in estimate of the distance itself. In case if you have continuous feature and you don't want to deal with computing approximate integrals, you can always discretize it by splitting its values into some buckets. Okay, so the most popular ones are, as written here, Kullback-Leibler distance and Pearson distance. And yeah, just to repeat once again, those values P and Q are sample-based estimations of the probability density function or probability mass function for those distributions of X. So P corresponds to this one, Q corresponds to this one. So let's take some example, which is a toy example. Let's build some model. So the model is written here, and it's just some really very simple example that anyone can program in Python in like 10 minutes. So you just generate, let's say, 50 features. Each one of them is discrete, takes just 3 values, and it is also uniform. And you build this like in a sense perfect formula. Perfect model, and then add some random noise to it, and the final model looks like this. So the final model is the y taking value either 0 or 1 based on some random noise plus something that depends only on x2, x3, and x5, and does not depend on everything else, even though we have already generated it. So for each feature, we just compute this Pearson distance. So here is the formula. Here is the same formula, but I replaced here each Q and P with the corresponding sample-based frequencies. And when we calculate those frequencies and plug them in, we can see that we have the following values for n equal to 500, the size of the sample. So for 500 x1s, 500 x2s, etc., and 500 y's that we calculated from those features, we get the following distances. And what is nice is that it worked basically, and the largest distances for the features that actually affect the variable y. And for everything else, the largest distance that we get is like almost 2.5 times lower than the value of the distance for x5 in this example. And what that actually means, this is just numbers, but what that actually means, it means this. So the idea is that these numbers represent how different distributions for two subsamples are. So for example, for the feature x2, you can see that the distribution of the feature x2 among those that gave y value equal to 0 objects is like completely different to the distribution of x2 among those like feature vectors that gave value of y equal to 1. So the same is true for x3, the same is true for x5, even though they look a bit closer. But if you take like random feature x25, which does not participate in constructing y, then you can see that distribution is approximately the same. It's like very close. Even for 500 observations, it's already enough to see that x25 is distributed in approximately the same way within both groups. So those histograms are not normalized, but still you can see it. If you normalize them, it's even more clear. So yeah, just to repeat once again, the idea is that if some characteristic of objects is distributed similarly within two groups that we try to distinguish, then probably this object is useless. If some characteristic is distributed differently within two groups that are built based on the feature, based on the target that we're trying to predict, then probably it is useful to include such an object to the sample, to the model building process. So some benefits, just to repeat, it's lightweight in a sense that it's just a couple of formulas and estimation of probability density functions. That actually means building some histograms. It's fast because it does not require any model building. It does not require any complex analytics. So it can work well with large data sets when the number of features is actually huge. And in medical studies, the most common situation when it is used is genetic studies. It is easy to integrate into any feature selection method and into any existing data pipeline with minimal additional overhead. It supports any features and it allows to compare them between themselves without special handling, without any complex transformations of categorical variables like one-hot encoding. And it is easy to interpret it because it's just easy to understand what is actually happening behind the hood. And it does not require any assumptions. So I didn't say anything about the model itself or about the distribution. It does not require any parametric formula. So it's fully assumptions free. If you want to prove some properties, of course, you need to make some assumptions, but just to implement it, you don't need any modeling. So some applications is that like churn analysis, or to make it more broad, I would say any model in which the event of interest is actually rare compared to the size of the sample. It is used. It can be used in A/B testing, and it allows to better understand A/B tests results. And yeah, medical studies again, just because it works well with case control studies because it relies only on conditional distributions within groups and does not rely on the on the sizes of the groups being representative of the frequency of the target variable. Yep, and some takeaway. That was a model-free and statistically grounded method for imbalanced binary data that works fast and easy to interpret. It is ideal for insights for minority obtained from minority classes, and it is easy to explain and easy to use. So that's all from me. Thank you very much again. I hope that was clear and interesting.
Sergey, for sure. Thanks for introducing the topic for us. Probably the implementation on the practical approach, the practical implementation is the topic of its own. How to deal with how to enrich our data pipelines with this method. But if you could share just like a glimpse intro on how to best do it. So do we introduce it as a kind of profiling? Do you and then it goes through the pipeline, or you stop the pipelines on certain conditions? How would you suggest to implement it?
So in my experience, this is a fully preliminary step to actual model building. So it's in between of the analytics and the data pipelines that store and like build the logs, for example, or transform the existing data tables. So the best way is just to, in my opinion, is to plug it into like this step of pre-processing and do not really rely on the model or the like properties of the data itself. So yeah, in my experience, that in case for telecom machine learning building pipeline that was a step that pre-processed the feature target metrics before actual model building process started.
Okay, so more like yeah, for the model building, but not rather a subject for kind of let's say automatic pipelines that adjust the models or prevent model drifting, something like that. So it's more for the experimentation and then model building.
Yes, I guess yeah, I wouldn't maybe it can be used to compare the distributions of within the same groups between different samples as well. So for example, the data arrives, some new data arrives, and you are trying to understand whether you are interested in an automatic model rebuilding due to the drift that happened. In that case, you can actually compare the distribution within, let's say, the same group y equal to 0 for the new sample that you achieved compared to the one that was used last time for modeling. And if you see that the distances of features that you obtained is very different, and even if you would run your pipeline right now, you would even get the different set of features that you would use, then it can be used as a flag confirming that the model should be retrained based on the shift that happened in the data. So I mean it can be used for that as well. I didn't do it personally, but I mean, why not?
Yeah, anyway, like any method to ensure that your data is correct is, I think, useful, right? For
Yes.
for the model building and for the quality. Sergey, thank you one more time for the presentation. Please, guys online, please give us a feedback about the talks. And right now, I'm going to have a longer break. And yeah, see you after the break.
Thank you very much. Bye bye.